All right, you guys, this is one of my most exciting moments of the entire year. And I'm so sad that we're doing this online because I just get a little giddy when we start talking about statistics. So, my hope is that some of this giddiness is going to flow over into our time together in class. But I do want you to have some of these videos as resources to help you both learn about what each of the statistics are and more importantly, how they all fit together into the broader question of what is statistical analysis even doing? So I will tell you this from the very beginning. If you were to either learn how to perform each one of these statistical operations or were to learn what is statistics all about, what do these numbers even mean, why are we doing this? If I had my personal choice between those two, I would prefer that you take away from this what statistics actually mean and what they're all about and forget how to do them because you can always relearn how to do them, but once you get what statistics are, that will never leave you. It is delightful, and I still remember the first moment. In fact, it was on the night before I was going to teach my very first Psych 3091 statistics class. And I was trying to figure out, okay, how do I explain this? And how am I going to help them to get this? And all of a sudden, I was looking at it. And for the first time in my life, now I'd been through high school, through undergrad, through 6 years of graduate school statistics. And the night before the first day I was going to teach this class, was the first night that I had my aha moment. Like, I think I just understood all of statistics. My hope, my deep and abiding hope, is that at least some of you, maybe even all of you, are going to have a moment like that in this class. So, my hope is I'll provide that for you. With all that to say, let's dive in. And the very first statistic we're going to talk about today, we're going to talk about the chi-square statistic. We're going to do this for a couple reasons that'll become obvious, but I want to state them ahead of time and we'll come up again in just a little bit. The first reason is because it is the simplest of all of them to calculate. So the chi-square is easy to calculate. The second reason is because it works with the most basic levels of measurement. We're going to talk about that. That'll actually be the first thing we get into in just a second. But the third of them is because all of statistics is contained in these three letters, O, E, and D. And really D, deviation, is just O minus E. And that's really all that chi-square is about. So I've talked about observations, expectations, and deviations. And what we're going to see is those actually show up in this statistic. So I want to use this to orient us to the entire field of calculating statistics. Okay, so let's go back to this levels of measurement question, because last semester we talked about levels of measurement. So first of all, try to quiz yourself for a moment. Pause the video in just a second. See if you can remember all four levels of measurement. I'll give you one of them and see if you can come up with the other ones. Nominal. Okay, see if you can come up with the other three levels of measurement. Okay, if you weren't able to come up with them, nominal is the most basic. Then we have ordinal, interval, and ratio. So as a brief review, nominal is where numbers basically just stand in for names. So like male versus female, you could code those. You could code males 1 and females 2. You could code males 1, females 0. It doesn't really matter what the number is. The number stands for a name or for a category of people or objects or events. Ordinal variables are where those variables, where the numbers signify what order they occur in. So you could think of this as like first, second, third place in a race, or the tallest, the second tallest, and the third tallest. It may be that the person who come in first and second in a race are only separated by 1/100th of a second, and the third place person finished a minute later. But they're still first, second, and third in terms of order. Interval is where the differences between the numbers actually start to make a difference. So first place, second place, third place, the distance between second and third place, like we just said, could be huge In interval variables, the distance between someone who scores a 1 and someone who scores a 2 is the same as the distance between someone who scores a 2 and scores a 3. They each have an interval of 1 between them, and those intervals are meaningful. And the last kind of number is, or level of measurement, is ratio. This is where 0 actually means something. So for me, the easiest example is the difference between degrees Fahrenheit, where once you hit 0 degrees Fahrenheit, you can just keep on going negative, negative 10, negative 20, and I'm well versed in this coming from Minnesota. We get way down below 0 lots of the year. Whereas in degrees Kelvin, once you hit 0, you literally cannot get any colder. Atoms stop. Everything stops at 0 degrees. So there's an absolute 0. Okay, so a little bit later in this class, we're going to learn a few different kinds of analyses that you do at the ratio level. These include things like the t-test, like correlation, like ANOVA, in fact, a couple different kinds of ANOVA that we'll talk about, and multiple regression. Now, it turns out you can actually use most of these tests with very little problem with interval level variables. In fact, most of the variables we use in psychology are closer to interval than they are to ratio. There's also analyses that you do with ordinal that we're not going to cover in this class. One of them is Rho, Spearman's rank order calculation, but we won't talk about it. The one we will talk about today is ChiSquare. And ChiSquare is the analysis that we use when our variables of interest are nominal variables, when both of them are nominal. So we're going to think about simple two-variable chi-squares for this class. It can get more complex. You can have 2, 3, 4, 5, 6 variables. What we're going to think about is two-variable chi-squares. Okay, so what kinds of questions involve two nominal variables? So both the grouping variable and the outcome variable must be nominal. So first of all, I'm going to pause the video and try to think what kind of a question involves two different groups of people that are having some kind of an outcome that's an either or where they come out as this or this or this. Okay, here's a few examples. Are children more likely than adults to say that they enjoy animated films? Say that they enjoy is either yes or no. If we asked how much they enjoy it, now this is an interval or a ratio. So this doesn't work for chi-square. Likelihood of saying yes or no is a nominal outcome variable. Here's another one. Are homeowners more likely than apartment dwellers to own dogs rather than cats? In other words, homeowners versus apartment dwellers, that's one nominal variable, that's our grouping variable. And dogs rather than cats you could think of as an outcome variable, or it's another grouping variable. Dog owners versus cat owners. And we want to know, are the proportions of homeowners who own dogs versus cats different than the apartment dwellers? Here's a third question. Are females more likely than males to take one class versus another? In fact, this is a question we're going to come back to in just a moment. So let's take a look at this. This is males versus females in what used to be Psych 391, now it's 3091. So I'm going to give you just some classes. I looked up one year, the males versus females in 3091 and Physics 311, which is modern physics. Okay, here are the numbers for that year. The question is, are females more likely than males to enroll in Psych 391 as compared with Physics 311? The sample was, not this class, but this is the class of 2012. I did this every single year for about 6 years, and then I stopped doing it because I had to change, because the way I did it, I had to change 25 slides every time I did it, and I'd always make a mistake, and that caused more problems than just using an old class. I'm going to use class of 2012. And here were the numbers that year. So in 391 that year, we taught 21 people instead of the smaller class size of about 15 or 16. And in that class, we had 15 females and 6 males. Now that's actually, as you'll notice, different from this year. In Physics 311 that year, there were 4 females and 11 males. And what we want to know is, are these proportions of male to females different between these two classes? Well, obviously, just by looking at it, they seem a little bit different, right? In 391, we seem to have a lot more females than males. And in Physics 311, they seem to have a lot more males than females. But maybe this is within the realm due to chance alone. And that's what we're really going to ask. So first, what we want to think about is observation and expectation. Like I've said before, and I'm going to say it again, all of statistics is based on a simple type of comparison. The comparison between our observations and our expectations. The easy part is our observations. This is the data that we actually collect. So for our question, we'd simply tally the number of males and females in each class, which is what we've done here. Each of these numbers is called a cell value, or sometimes an observed cell value. That's the observations there. So our first question is, how many females versus males do we actually observe in each class? Did these seem to be about equal or quite different? Now the trickier part is going to be figuring out, so those are going to be our observations. The trickier part is going to be figuring out what we expected the data to look like. So to calculate our expected value, we first need a couple more numbers. These are the row totals and the column totals. So here you see the row totals on the right. These are the row totals. And you see the column totals on the bottom. What is this other total right here in the corner? This is called the grand total. This is the total number of students in both classes combined. So here we have 21 in Psych 391, 15 in Physics 311, and that gives us 36 total students. Or if we want to break it down another way, in our total sample we have 19 females plus 17 males equals 36 total students. One way to think about our observations and our expectations is in terms of percentages. So what percentage of Psych 391 students are male versus female? Well, what we do is we calculate, so the way we calculate this percentage, just as a review of how to do percentages, is we do, for instance, for this one, we do 15, the number of females in the class, divided by 21, the total number of students, and that gives us about 0.71, which translates into 71%. So in Psych 391, we have 71% versus 29% in that class. How about in Physics 311? Well, in this class, we get 27% female versus 73% male. Now let's think for a moment about the null hypothesis. Remember this? This is like the bummer at the party that says something like this. There's nothing different about physics and psychology. This is just random chance. These are essentially the two classes are essentially the same in terms of the male to female ratio. If you see little differences, that's just due to little fluctuations in it. The null hypothesis is that the two samples or the two classes do not differ from one another here with respect to males versus females. Sadly, when we think about statistics, our expectations are defined by this null hypothesis. So statistically speaking, we expect that the two classes will be no different from one another with respect to their gender ratios. That's the null hypothesis. So, using the total sample as a guideline and assuming that each class stayed the same in terms of its numbers, so if we want to use this total sample of males and females as a guideline, how many females and how many males would we expect to be in each class? Well, one of the ways we want to think about this is we want to think about these percentages. If all of our sample is 53% female, then for each class, we would expect 53% of our class to be female. Okay? So let's take a look at how we actually calculate that out. So here, what we've done is we've taken because females make up 53% of the total sample, what we've said is, well, what would these classes look like if the null hypothesis was true? What is our expected value for each class? And here, because we have 21 total participants, what we do is we take 0.53 times 21, in other words, 53% of this class should be female. So our expected value is 11.1. Right here, the way that we've gotten that is 0.47 times 21. And that gives us 9.9. Now we've done the same thing over here. 53% of 15 is 7.9. 47% of 15 is 7.1. Okay? So these are our expected values. So the next thing to ask is, how would we describe the difference between the expected and the observed? Remember, the three components of statistics are our observations, those are the actual numbers in each class, our expectations, that's what we calculated here, and the deviations. This difference is called a deviation, the difference between our observation and our expectation. O minus E equals our deviation. Okay, so let's take a look. Here are our observations and our expectations. The observations are these numbers, and the expectation, the expected values that we just calculated, are in parentheses here. So what we want to do is we want to compare the two values in each cell. So the question is, do these differences look like they happened by chance? In other words, that more females just happened to sign up for the Psych 391 class, but that it would even out in the long run? Or do these differences look like more than just chance? Well, this question of whether these differences happen by chance is what the chi-square is going to answer. We can think about the chi-square as a kind of mathematical judge of probabilities, or the likelihood that different ratios of people or events simply happened by chance. So the chi-square test, or simply the chi-square, measures the significance of the data in comparison with what you'd expect to get. The chi-square only requires that you know the number of individuals observed in each category and what numbers you expected them to be, the E value that we just did. So the chi-square formula is, get ready for it, take a deep breath. But the good news is you know all this. Chi-square is simply this. Okay, take a deep breath, because you know everything that's in there. Are you ready for it? Let's just break it down. We'll end this video and then we'll calculate it for the next moment. Okay, you know every part of this. First of all, O. O is the number of observed cases. That's the number of actual males and females in each class. E is the number of expected cases in each category. So for instance, our O for females in 391 is the number of actual females who are in 391. Our expected is the number that we expected if that gender ratio was like everything else. If it was that 53%. The symbol sigma is used throughout math to mean sum. So here, what we're doing is we're calculating the difference between our observed and our expected scores. This is called a deviation. We're calculating the deviation between our observations and our expectations. Then we're going to square the difference for each one. So here's our deviation. We're going to square the difference for each one. Then we're going to divide them by the expected score. What this does is it kind of brings it back down into range. So for instance, if we had 6,000 females, if we had one class that was like 10,000 people large, and we had 6,000 females and 4,000 males in there, and we're trying to compare that to a Psych 391 class that had 11, or 15 females and 6 males, we got to bring those down to a size that where you can compare it to each other. So we divide it back by that expected score. And then we just sum it all together. We sum together all the dividends together. So in the next video, we're actually going to do this, and then we're going to